Co-21A. Today is January 11th, 2024. This desk could be a little bit higher. Great. Okay. So when it comes to trig functions, let's start with sine. So we're going to graph y equal to sine of x. And there's a couple ways you could go about doing this. I would start with this. So there are usually, when I'm graphing the sine function, 5 points I'm interested in plotting. I'm going to plug in the quadrantal angles. In fact, what I'm going to do is I'm going to think about my unit circle. And just like last class, I'm going to think about drawing the 4 corners. Yes, I know, corners of the unit circle. The point 1, 0, the point 0, 1, the point -1, 0, and the point 0, -1. I'm also going to write in the angles that go with that. So over to the right is the angle 0 radians. Up here is pi over 2. Over to the left is pi radians. Down here is 3 pi over 2. And then if you go make a full revolution, it's also 2 pi radians. We could also throw in the degrees just to see them. This would be 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. But when we graph things, we're certainly not saying the x-axis is measured in degrees. Right? The x-axis is measured in units that don't really have a dimension, which is why radians are ideal, because radians don't have a unit or a dimension. It's kind of weird when you think about it, but it's true. Because when you're measuring a radian, you're actually measuring the arc length that that your angle has subtended divided by the radius. And so if you're dividing a length by a length, you know what happens to those units? They cancel out, and there's no units. Kind of weird, but kind of neat. Yeah. Oh, yeah. You're always welcome to leave and come and go as you need, use the restroom, take a phone call, whatever. Yeah, totally fine. Anyone, you never have to check in with me. Just come and go as you want. I know it might be challenging in the sea of desks over there, but you're always welcome to exit and enter as you wish. So graphing this, I'm going to plot some points. So my angles are my x values. So I'm going to say 0 radians, pi over 2 radians, pi, 3 pi over 2, and 2 pi. And my y values in this graph are going to be the sine values, which are the second coordinates of each of these points. So sine of 0 radians is 0. Sine of pi over 2 radians is 1. Sine of pi radians is 0. And then -1. And then 0. So those are the 5 points I'm typically going to plot when I'm thinking about graphing the sine function. Could I plot more points? Definitely. Am I going to? Usually not. So I usually like to mark out about where 2 pi is going to be. Really, I'm just picking a spot that's easy to break up into 4 equal quarters. So I'm going to chop that in half and then chop each of those in half again. So that's pi. There's pi over 2. There's 3 pi over 2. Usually when I graph this, my y-axis is maybe not quite to scale with my x-axis, because that length there, pi over 2, is about 1.5. It's a little more than 1.5. But that's probably about how big I make my value of 1. Not for any good reason. It just ends up looking a little bit nicer, I feel like, when I do it that way. But really, you can scale things however you like. So I'm plotting the point 0, 0, pi over 2, comma 1, pi, comma 0, 3 pi over 2, comma -1, finally 2 pi, comma 0. And here is 1 period of my sine graph. 1 period and a little bit more on the end, right? We usually don't just like stop at the ends. We kind of draw arrows to indicate that it keeps continuing in both directions. And it would look the same, right? If I graphed another period, in fact, let's go ahead and graph one more period. It's going to do the same thing. So I'm going to take that length from 0 to 2 pi. I'm going to translate it over there. So about right there, and do the same thing. So the sine graph repeats. It's going to go up to 1, back down to 0, back down to -1, back up to 0 again. But that's why we only graph 1 period of it, because once you've graphed 1 period, you kind of know the whole story. It's just going to keep doing the same thing over and over and over and over and over again. Oh, that's a little, interesting. It's a little sharp there. File that down. Let's see. What do you want to say about the sine function? The domain is all real numbers. There's no x value you can't plug in. The graph certainly would indicate that, right? It doesn't look like there's any places where the function seems to be undefined. So our domain is everything. Our range, on the other hand, is much more limited. The range, we go as low as -1, as high as +1. What are some other interesting properties of the sine function? Like many functions, like most functions, I would say, it is continuous. There's no breaks. Or as people often say, I could draw the graph without lifting my pencil off the paper or pen or whatever you're writing with. And also, although we haven't defined this yet in this class, or we haven't defined anything really, it's also differentiable. Meaning the derivative exists everywhere. Graphically, what I would encourage you to think of is when a function is differentiable, it's smooth. There's no pointy parts. There's no corners. There's no cusps. And in fact, just as a kind of counterexample of a function that is not smooth everywhere, that is not differentiable everywhere, y equal to the absolute value of x. Looks like kind of like a really wide V. And definitely it is pointy at the origin. That graph has a sharp turn. This graph is not differentiable. Let me contextualize that just a little bit. I said that graph is not differentiable. Really, that's kind of not the whole story. That graph is actually differentiable almost everywhere. There's only one point where it's not differentiable, but that's enough for us to say, when someone asks the question, is this differentiable? We would say no, it's not differentiable everywhere, so it's not considered to be differentiable. Specifically, it's not differentiable at x equal to 0 because there's a corner there. Or a cusp. This is actually specifically a corner. It's a hard right turn, left turn, whichever way you want to think about it. Cusps are a little bit different, but we'll talk about those in a bit as well. Is this function continuous? Did I have to lift my pen off the paper when I drew it? No, it definitely is continuous everywhere. Although I don't really need to say the everywhere part, because when I say it is continuous, the everywhere is implied. Just like when I say it is not differentiable, the everywhere is also implied. It's differentiable almost everywhere, but not everywhere. Oh yeah, there was something. Yeah, we'll come back around to that. Oh, one more. Yeah, that was like there's one more property I wanted to mention. This function also happens to be odd. No, it's not strange, although maybe you think it is. Specifically, it has a property meaning that it has what we call rotational symmetry, or if you prefer, symmetry about the origin. So odd means graphically we have rotational symmetry, which is kind of hard to see because I haven't graphed the left side of this. Also known as symmetry about the origin. You can either think of it as literally rotating the graph around the origin 180 degrees and it looking the same, or reflecting it in both the x-axis and in the y-axis and it looking the same. And again, right, if you continue this graph to the left here, give you a little bit more of a picture here to deal with. You can kind of see, oh yeah, if you rotated this thing 180 degrees, it would look the same as it originally looked. Or if you flipped it that way and that way, it would look the same as what you started with. We'll contrast that with an even function in a moment. I'm trying to get out of the practice of saying, do you have any questions? But you should all know you're welcome to ask questions anytime. So if you have questions, don't hesitate to ask. I'm happy to clarify, answer questions. Or if you have a correction because I made an error, which will happen, I promise you I'll make some mistakes. Please don't wait like 10 minutes later. You're like, James, I think you made a mistake. Yeah, I probably made a mistake. If you think I made a mistake, I probably did. If I didn't, I will also be like, oh no, it's this because of this. But often, if you think there's something, if you might ask the person next to you, did he make them? Yeah. James, you made a mistake. I don't try to make mistakes, but you know, no, it's perfect. Let's look at the cosine function and we'll say a few things. And what I should do is I shouldn't draw that four corners of the unit circle again. I should just go back and look at it because why do I need to do it again? Here's my four corners of my unit circle right there. And if I'm going to try and graph now cosine of x, I still want to use the same 5 angles, 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. But now I'm going to use, well, the x values for the values because x is the cosine. So cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is 0. Sorry, is 1. Oh my goodness. Look at the wrong thing. Now look at the right coordinate. So now we're going to graph that. And the thing about this is it's going to look very much the same as cosine. In fact, it's sine. It's almost exactly the same. It's just shifted pi over 2 in one direction. And I'll try to leave myself some room to draw the left-hand side of this as well. But just, oh, wow, that is not the straightest line I've ever drawn. So breaking this up into 4 equal quadrants or 4 equal quarters. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi gets you back to where you started, which was the value of 1. It's going to have the same sort of shape. But whoops, it's going to look, ooh, geez. Not my best graphing ability there. But it's going to look like the sine function just got shifted pi over 2 to the right. Come on in, have a seat. There's plenty of seats. So here's y equal to cosine. Same domain and range as sine. Right? Its domain is also all real numbers. Its range is also everything from -1 to 1. It is continuous. It is differentiable. And unlike sine, it is an even function. So cosine of x is an even function. It has symmetry about the y-axis, meaning if you reflect it across the y-axis, it looks the same as it did originally. And if I graph a little bit more of it to the left, you can see that. Right, if I reflected that across the y-axis, it would look the same. Just because sometimes people ask, there is no symmetry. Well, there are very, very, very few, literally only one, functions that have symmetry across the x-axis. You can't really have symmetry across the x-axis because if you do, you're not a function. Right? Think about like, I'm going to draw on the board. Think about something that looks like this. Like x equals y squared. It certainly has symmetry across the x-axis. In fact, you guys see that too. Maybe you can see here. See there's my x equals y squared. See, lovely. Has symmetry across the x-axis, but not a function. Right? Fails the vertical line test. There is one function. It's kind of silly that has symmetry across the x-axis. It's f of x equal to 0. There it is. And if you flip it across the x-axis, it still looks the same. It's the only one. It's not a thing we talk about. You don't talk about a function having that kind of symmetry because it doesn't make any sense. It's not a function if it has that kind of symmetry, with one weird exception. Speaking of symmetry, just to kind of take a departure here, these functions are not great for showing how you determine if a function has even or odd symmetry, or neither. So let me give you 2 examples of functions that are easier to show that they're odd or even. So let's look at this function. F of x equal to, let's just do with x squared. So if x equal to x squared, let's make it x squared plus 1. So I'm going to graph it. All right. What do we think? Even or odd? Do thumbs up for even, thumbs down for odd. Is it even or odd? I want a thumbs up for even, thumbs down for odd. I see a few thumbs. Okay. Yeah, I'm seeing mostly thumbs up, and it is. It's definitely an even function. It has that symmetry across the y-axis. If you reflected it, it would look the same. Or you can kind of think about it like this half of it over here is looking over there and seeing its mirror image. It's an even function. Now, how do you show it's even? To show it's even, by showing that f of negative x is equal to f of x. Which is not too terrible to do. If I take my original function and start with a negative x in for every x, f of negative x is negative x quantity squared plus 1. But negative x times negative x is positive x squared. So this ends up equaling positive x squared plus 1. And that is f of x. And that shows that this is an even function. We can't just do it for one number, though. Like if you show that f of 3 equals f of negative 3, that is supporting evidence that it's an even function, but that actually doesn't actually prove it's an even function. So you have to show that this is true for any x in the domain of the function. Let's look at an odd function as well. Here's an odd function. Example. G of x equal to, yeah, sure, let's do that one. X cubed minus x is definitely odd. Let's graph it. So it's going to look like a cubic function. It's got intercepts at -1, 1, and 0. Which you could find by setting x cubed minus x equal to 0, factoring out an x, and then factoring x squared minus 1 is x plus 1 times x minus 1. And that's how I got the 3 intercepts. And here's what the graph looks like. Vaguely. And the graphing skills are always a little suspicious. But I will say, assuming you can believe that I've drawn this symmetrically, it does have this odd symmetry. You could either rotate it 180 degrees around the origin and it would look the same, or you could reflect it in the x-axis and then reflect that in the y-axis and it would look the same. And then we check to see if something is odd. So to check for oddness, or for whether a function is odd, we have to check that f of negative x is equal to negative f of x. Some people phrase this slightly differently. I like doing it that way, but some people might phrase it as checking to see that negative f of x, sorry, negative f of negative x is equal to f of x. To me, that just feels weird. I don't know why. It's really the same thing, but whichever way you like, totally fine. So here, if I want to check that this was odd, I would look at g of negative x, and I would get negative x quantity cubed minus negative x. And then I would simplify it. Negative x times negative x times negative x is negative x cubed. Minus minus x is plus x. From here, you can either try like factoring out a minus sign to see that it's equal to negative g of x, but I think it's easier just to then in the next line write what negative g of x is. Negative g of x is negative all of g of x. And then the minus sign distributes across subtraction. So it's going to be negative x cubed plus x. And those are the same. So it works out. This is definitely an odd function. The reason I bring this up in the context of sine and cosine is because it's not as easy to show this way that sine and cosine are respectively odd and even. It's true, but you have to use like the angle sum formula. It's kind of a big pain. So I'll just point out sine of x is even. Sorry, oh my God. What is sine of x? Not even, it's odd. Don't let me, I mean, sometimes I say dumb things. Sometimes my brain starts thinking of the next, like I was already thinking of saying cosine was even. So I was like, oh, sine is even, because I got too far ahead of myself. Sine of x is odd, which means that sine of negative x is equal to negative sine of x. It's kind of useful, actually. If you have to find like sine of negative pi over 3, I don't like thinking about quadrant 4. I'm going to say, well, that's equal to negative sine of pi over 3. And sine of pi over 3 is the square root of 3 over 2. Which makes sense if you think about it, because if sine of pi over 3 is root 3 over 2, sine of negative pi over 3, which is in quadrant 4, should have a negative value, because sine is negative in the fourth quadrant. And it should have the same numerical value, just negative instead of positive. Cosine of x is even, which means that cosine of negative x is equal to cosine of x. For example, cosine of negative pi over 3 is equal to cosine of pi over 3, which is just positive 1/2. That also, in my mind, makes sense when you think about the quadrants. If you have an angle in quadrant 1, cosine is positive. If you have the same angle in quadrant 4, cosine is still positive, because cosine is positive in quadrant 4. Excuse me. All right. 2 down, 4 to go. Let's talk about the other 4 trig functions. We will probably not be super detailed with them just because, I don't know. I mean, their graphs are important, but they're not that. They're kind of important. Let's talk about tangent. So we're going to graph y equal to tangent of x. Which I always feel like is kind of, I don't know, just strange. So if I was graphing tangent, here are the values I would look at. I would start with the following angles. 0. I'm going to leave some space to fill in some intermediate ones. Pi over 4, pi over 2. And then I would also go negative. I would go negative pi over 4 and negative pi over 2. Yeah, I know pi over 2 is a bad, it's not a bad choice. It's just it's not going to have anything nice. The tangent of 0. I don't remember what tangent of 0 is. I know the tangent is sine over cosine though. So I know that's going to be sine of 0 over cosine of 0. And we just found those in the previous 2 problems. That's going to be 0 divided by 1, which is 0. I love tangent of pi over 4 because tangent of pi over 4 is just sine of pi over 4 over cosine of pi over 4. I don't even really want to write them down because I know that sine of pi over 4 and cosine of pi over 4 are the same. Right? Pi over 4 is the angle of 45 degrees where y equals x. If we're on the line y equals x, then the sine value and the cosine value have to be the same. You could also write them down. It's equal to the square root of 2 over 2 divided by the square root of 2 over 2. But when you divide something by its own self, with one exception, you always get 1. Root 2 over 2 divided by root 2 over 2 is 1. 3 over 3 divided by 3 is 1. 5 divided by 5 is 1. 7 divided by 7 is 1. What's the exception? 0 divided by 0. 0 divided by 0 is not 1. It's not 0. It's not anything, really. It's an indeterminate form, which you're going to see a lot of. Because when we start talking about limits, a lot of these limits are going to end up having a 0 over 0 form when you plug in the value. And then you're going to have to do some algebra and make things work out. Okay. And then tangent of pi over 2 is unfortunate. It's sine of pi over 2 over cosine of pi over 2, which is indeed 1 over 0, which is undefined. We're going to get a vertical asymptote there. We have division by 0. And when you have not 0 divided by 0, that almost always means you have a vertical asymptote on your graph. Same thing to the left, except now we have negative values. Tangent of negative pi over 4 is sine of negative pi over 4 over cosine of negative pi over 4. From what we just said about even and oddness, sine of negative pi over 4 is the same as negative sine of pi over 4, which is negative root 2 over 2. And cosine of negative pi over 4 is positive root 2 over 2. So we end up getting a negative 1. And then just like pi over 2, negative pi over 2 tangent is also going to be undefined. Sine of negative pi over 2 is negative 1. Cosine of negative pi over 2 is still 0. That's still undefined. So let's see what we can plot. So let's say that's pi over 2. So that's negative pi over 2. Draw ourselves some asymptotes. This thing I'm writing on is not super stable. It's a little wobbly there. Okay, well, maybe I'll get a piece of paper later on. But sorry, anyway. And then a pi over 4. Pi over 4. So when I'm graphing things, I'm trying to make the scale look nice. I'm thinking pi is about 3. So pi over 4 is about 3/4. So if I'm trying to plot 1 on the y-axis, I'm kind of going up over there and saying that's about 3/4. 1's a little bit higher. And then same deal down there. So now I'm going to go down there and be like, there's a negative 1 about there. So tangent of 0 is 0. Tangent of pi over 4 is 1. And then as we get closer to pi over 2, the tangent values get larger and larger and larger. Similarly to the left, tangent of negative pi over 4 is negative 1. Tangent, as we get closer to the vertical asymptote, we're going to go down, down, down to negative infinity. It's going to look kind of like this. I've drawn it better before. Oh well. There's our tangent graph. I should say, there's one period of our tangent graph. Because after this, it just starts doing the same thing over and over and over again. So unlike sine and cosine, and cosecant and secant, tangent has a period of just pi. It takes a length from negative pi over 2 to pi over 2 to start repeating itself, which has a length of pi. So if we draw one more period here, let's see if we can move that over there. Yeah, sure. Just trying to eyeball it. Here's another period of tangent. Should look the same or as close to the same as you are capable of drawing it. And same to the left over here. One more period. Back. Pi, pi. So there's like 2.5 periods of tangent. Let's talk about some of the features of tangent. And let's skip the domain for a second because the domain's kind of annoying. Let's talk about the range. The range is everything. You get all y values as low as negative infinity all the way up to positive, right? You're not missing anything. And the domain is we're missing every odd multiple of pi over 2. We're missing 1 pi over 2. We're missing 3 pi over 2. We'd be missing 5 pi over 2, negative pi over 2, negative, right? All the odd multiples of pi divided by 2. So you could either write this way. You could say, well, it's like negative pi over 2, comma pi over 2, union pi over 2, comma 3 pi over 2, union, and then kind of dots, right? This is not terrible to write that, but still kind of annoying. The way you'll probably see it written in a textbook or by a professor is as like this. They're going to say negative pi over 2 plus k times pi, comma, positive pi over 2 plus k times pi, where k is an integer. So 1, 2, 3, negative 1, negative 2, negative 3, etc. So if k is 0, I get negative pi over 2 plus 0 to pi over 2 plus 0. K is 1, I get negative pi over 2 plus pi, which is pi over 2, to pi over 2 plus pi, which is 3 pi over 2, and so on and so on and so on. Is this function continuous? Definitely not. Right? It's definitely, it can't even be continuous. And I know we haven't talked about the definition of continuity yet, but I will point out that a function can't be continuous if it's undefined somewhere. Being defined is a precursor to being continuous. So definitely not continuous. So it's not continuous everywhere. Is it differentiable everywhere? Also no. Because just like what I said before, and again, this is something we haven't learned yet, but I'm going to say it. Continuity is a requirement for differentiability. A function has to be continuous to be able to be differentiable. It has to exist. It has to be defined to be able to be differentiable. So definitely not. But I'm going to say something extra here because this is actually what we really care about. Although this function is not differentiable everywhere, definitely not at pi over 2 or 3 pi over 2 or any of the places where there's a vertical asymptote. Like most functions, it is differentiable on its domain. So wherever this function is defined, it is continuous actually and differentiable. So that's something that people say often. And I just want to point out this function f of x equal to tangent of x is continuous and differentiable on its domain. And that is often, so like, for example, people also talk about rational functions that way. So like x over x minus 1. Yeah, it's not defined when x is equal to 1. But aside from that, it is continuous and differentiable everywhere that it is defined. It's kind of interesting. Let me ask you all. You write down your answer. Is this function even or odd? Oh, I should say one more thing, actually. I didn't give you all the options. Is this function even or odd or neither? Because neither is always an option as well. Functions don't have to be even or odd. They could be neither of the two. All right, let's think about this here. It doesn't look even to me, because if you tried reflecting it across the y-axis, it wouldn't look the same anymore. If I tried rotating it 180 degrees around the origin, I think that would work out. It definitely is an odd function. So, yeah, I don't know where to write this. Sure. Tangent of x is an odd function. And you could show it by exploiting the fact that we know that sine is odd and cosine is even. In fact, we should do that because it's good work. So to show it, we're going to do this one together, but when we do the next one, make you do it on your own. So to show tangent is odd, I'm going to look at f of negative x, which is tangent of negative x. I'm about to use the fact that I know what sine and cosine are, odd, even wise. Sine is an even function, which means sine of negative x is going to equal negative sine of x. Cosine is an even function, meaning cosine of negative x is going to equal cosine of x. And just to make sure, I did say sine was an odd function, right? I feel like I'm hearing it back in my head, and I might have said sine was even, which was terrible. I meant to say sine was odd if that's not what I said. Sine is odd. Sine of negative x equals negative sine of x. Cosine is even. Cosine of negative x equals cosine of x. But then negative sine divided by cosine is negative tangent. So tangent of negative x is equal to negative tangent of x, which means tangent is odd. Kind of cool. Kind of slick. All right. What time is it? Yeah, we got time. Okay. What time do we end at? We end at 2:30. 2:30, right? Yeah, okay. It's hard to these hour and a half times always throw me off. I'm like, what time do we okay. If I go over, stop, don't let me go over. Be like, James, it's 2:30. Stop talking, please. I'll try the clock. There's a clock there, it's right. There's a clock here which I can kind of see. I should set an alarm, but not right this moment. Okay, let's look at the other one. So let's graph cotangent of x. Cotangent is just the reciprocal of tangent. Right? It's literally cosine divided by sine. So I'm going to pick different values because they're nicer. And yeah. So x cotangent of x. I'm still going to pick 0 and pi over 4 and pi over 2. But I'm actually going to end up getting a vertical asymptote at 0 because I'm going to have cosine of 0 divided by sine of 0. And cosine of 0 is 1 and sine of 0 is 0, and that's undefined. And I don't really want the asymptote to be the middle of the one period that I draw. It's just, you could do it that way, but we don't typically. I don't know why, it's just not nice. I'm going to draw my period from asymptote to asymptote. So I'm going to go from 0 all the way to pi, because pi is where I'm going to have my other asymptote. Cosine of pi divided by sine of pi is -1 divided by 0, which is also undefined. Pi over 4, we've already talked about how that's going to be 1. Cosine of pi over 4 divided by sine of pi over 4 is still √2/2 divided by √2/2, which is still 1. Pi over 2 is where we're going to get 0. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. 0 divided by 1 is 0. And 3 pi over 4, all right, let me ask everybody, show me on your fingers. What quadrant is the angle 3 pi over 4 in? I think I'm seeing a few too many fingers there. It's in this quadrant. So 0 radians, pi over 2 radians, pi radians, 3 pi over 2, not 3 pi over 4. So 3 pi over 4 is not quite as big as pi. Right? We haven't gone a full half revolution. That's terrible. A full half revolution, I know, is the wrongest thing to say. We haven't made a. There's not a better way to say it. We haven't made the half revolution. Right? We're not quite at pi. We're at 3/4 of pi. So we haven't made it out of the second quadrant. And in quadrant 2, which trig function is positive in quadrant 2? Did you guys not know the mnemonic device? Do I get to say it? Say the fun one. All strippers take cash. All students take calculus, I mean. That's what we're supposed to say. All students take calculus. So in quadrant 2, sine is positive. In quadrant 3, tangent's positive. In quadrant 4, cosine is positive. In quadrant 1, all of them are positive. So in quadrant 2, sine is positive, and by elimination, tangent and cosine are negative. So here we get -√2/2 over √2/2, which is still -1. We also could have just kind of cut out the middleman and said, oh, in quadrant 2, sine is positive, so is cosecant, it's reciprocal. And the other 4, including cotangent, have to be negative. So anything in quadrant 2, cotangent should be negative already. We shouldn't have to worry about which sine or cosine is. All right. Graph of cotangent is going to look very similar to the graph of tangent. Just like the graph of sine and the graph of cosine also look very similar. They're just kind of shifted from each other. This one actually looks more like it's reflected and shifted. Instead of going up from left to right, it's going to go down from left to right. So pi, asymptote here. At pi over 2, we're going to get 0. At pi over 4, we're going to get a value of 1. And at 3 pi over 4, we're going to get a value of -1. And so it's going to look kind of like this. And then it repeats. There's a little more than 2 periods of cotangent. Range is the same as tangent. Range is still everything. Here, the domain, now you're missing every multiple of pi instead of every odd multiple of pi over 2. So the domain is everything like 0 to pi, union pi to 2 pi, union 2 pi to 3 pi, and then the other way as well. Or you can say it's 0 plus k times pi to pi plus k times pi. Or you can say it's like k pi comma k pi plus 1, k plus 1, where k still is an integer. You don't really have to write the k as an integer part. If you write something like that, everyone's going to assume you mean that k is an integer. You can also use n. N is kind of the other typical choice. All right. Fun question. Maybe, I don't know, fun. Fun's, I think it's fun. You might think it's fun. Is this function odd or even? Which symmetry can you discount right off the bat? Yeah, not even for sure. If you try to flip it across the y-axis, doesn't look the same. Is it odd though? I mean, yeah, it looks odd. It is odd. All right, I want you all to show it. Take a minute and show that cotangent of negative x, which is cosine of negative x over sine of negative x, is going to equal negative cotangent of x. Actually do it. It's good practice. It's better practice if you can read what I'm writing, though. Failing to write large. You need to write larger. Could zoom into, I guess. Zooming in helps. Let's see. Cosine is an even function, so cosine of negative x should just be cosine of x. Sine's an odd function, so sine of negative x is negative sine of x. And cosine divided by sine is cotangent, so cosine divided by negative cosine. Oh my gosh, words. Cosine divided by negative sine is negative cotangent. That's it. It's odd. Yeah. All right. Two more trig functions. I know there's a lot. It seems like it doesn't seem like 6 should take this long to graph, but there's important features of all of them, so we should talk about them. The last two we'll graph relatively quickly here, and then we'll talk about a few more things about them, because there's one thing specifically I really want to say. So let's graph. What should we do first? Let's do cosecant. So y equals cosecant of x. Okay, let me show you my tried and true method for graphing cosecant and secant, which I think is wonderful. I think it's a good way of doing it. So instead, I'm going to first graph. Yeah, I'm going to normally okay. I'm going to graph the reciprocal. What is cosecant the reciprocal of? Is it sine or cosine? Sine, right? And the way I remember is whenever you have this reciprocal pairs, one of them always starts with a co, and one of them doesn't. Tangent and cotangent are reciprocals. Sine and, well, it's not secant because one of them has to have a co, so it's got to be cosecant. Cosine and secant. Those are the ones that are reciprocals. So cosecant of x is equal to the reciprocal of sine. And similarly, secant of x is equal to the reciprocal of cosine. It is also true, although less necessary, just as an FYI, you can also write that sine of x is equal to the reciprocal of cosecant. It doesn't come up as often, but it is a true thing. If one thing is the reciprocal of one thing, then the other thing is also the reciprocal of the other thing. They always go together. Like grammar lemon. Okay. None of that. So here's how I would try to graph this. I would start by graphing sine. So I'm going to break out my 2 pi. Let's go 2 pi to the left as well. I think I have enough room here, sure. And then I'm going to cut that up into 4 quarters. So pi, and then pi over 2, and then 3 pi over 2. And the same on the left as well. Cut that up in half as negative pi over 2, negative 3 pi over 2. Okay, so now I'm going to graph sine. Let's do it in red because we don't really want it. So sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0. Same thing to the left, sine of negative pi over 2 is -1, 0, 1, 0. When I think about graphing sine, I also think about, can you have this pattern where it's like in the middle, then the top, then the middle, then the bottom, in the middle, then the top, then the middle, then the bottom, in the middle, then the top, then the middle. You can make a song out of it. Middle, top, middle. Oh, I didn't want to draw it. I wanted to draw it dashed. Sorry. I don't really, that's not really what I'm graphing. Normally I would just plot these points actually, which I'll do for the next one. Okay, so there's my sine graph. So cosecant is the reciprocal of these values. What's the reciprocal of 1? Sine of x is equal to 1. 1 over sine of x is equal to also 1. So when I get a value of 1, the cosecant graph also has a value of 1. Okay, now here's a question you're going to hear me ask you a lot. In a fraction, if the denominator gets smaller, the overall value gets right. And vice versa. If the denominator were to get larger, the overall fraction would get smaller. That is something we all rely on a lot. We're going to use that fact over and over and over and over. So 1 over a large number is a small number. 1 over a small number like 0.00001 is a large number. So here's what I want to point out. As the sine graph gets closer and closer to 0, the cosecant graph is going to get further and further away from 0. It's going to get infinitely large. We're going to have a vertical asymptote right there, and the cosecant graph is going to go up, 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 up. The same thing is true to the left. As the sine graph gets closer to 0, the cosecant graph gets further away from 0. It is not a parabola, although it kind of ish a little bit looks like one. But it's not, and it's really not because parabolas don't have vertical asymptotes. But I know, when I drew this the first time, I was like, oh yeah, it kind of has a looks like a parabola. So it kind of has a parabola look, but not a parabola. Same thing over here. If sine of 3 pi over 2 is -1, what's the reciprocal of -1? What's 1 divided by -1? Yeah. Important fact also, reciprocals always retain the same sign. The reciprocal of a positive number is a positive number. The reciprocal of a negative number is still a negative number. Okay, so cosecant of 3 pi over 2 is -1. And then as the sine graph moves closer to 0, the cosecant graph moves further away from 0. Same deal over here as well. There's one period of the cosecant graph from 0 to 2 pi. Here's another period. So when I draw my cosecant graph and in a second my secant graph, what I really think about doing is drawing the reciprocal function, cosine here, cosine in the next one. And then essentially what I like to say is I flip it away from the x-axis. So this part that's kind of curling down towards the x-axis, I'm flipping it away from the x-axis. This part here that's curling up, I flip it down away. I'm always flipping it away from the x-axis. Okay, a few more things and then we will move on. The range here is kind of funky. The range here is almost, with one exception, it's everything that the sine function doesn't get. So the sine function range is everything from -1 to 1, and the cosecant function range is everything else, but also including the -1 and 1. So the range here is -infinity to -1 bracket. We're missing everything between -1 and 1, and then everything from bracket 1 to infinity. The domain here is the same as the domain for the cotangent function. We're missing every multiple of pi. So here our domain is 0 plus k times pi to pi plus k times pi. Exclusive. K is an integer. Okay, instead of writing K as an integer, you might see your instructor write K is an element of fancy Z. It means the same thing. Fancy Z is the set name for the list of integers. I don't know why they picked Z, but Z is what they picked. Just like fancy R is the set of all real numbers. So I don't typically use that notation, but in case your professor is, that's what that means. That's, the set from -3, -2, -1, 0, 1, 2, 3, forever and ever and ever. All the counting numbers and 0 and all the negative counting numbers.
Can I ask a question?
Yeah. Sorry, let me turn it up here. Just one second.
Okay, thank you. So how did you figure out that pi and 0 is the asymptote for the cosecant graph?
Good question. So the way I figured it out was I know that sine is equal to 0 there. So sine of 0 is 0, sine of pi is 0. But then the cosecant graph is 1 divided by sine. And we have seen in the past that we get a vertical asymptote when you have a fraction where you're dividing by 0. So the fact that we're getting 1 over 0 at pi and 1 over 0 at 0 and 1 over 0 at negative pi, that's what's informing us about our vertical asymptotes.
Okay. And then another question that came up was the domain. I don't really understand what the 0 plus k. What is
Sure.
k?
So K is any number. So this is just a way of writing it without doing all the writing. So what I'm really saying here for this domain is K could be anything. So if K equals 0, I get 0 plus pi, sorry, 0 plus 0, because K is 0, not 1, to pi plus 0, which is just 0 to pi. And then when K is 1, I get 0 plus pi to pi plus pi, which is everything from pi to 2 pi. When K is 2, I get 0 plus 2 pi to pi plus 2 pi. So every time I increase K by 1, I get the next, here's 0 to pi. Here's
Okay.
pi to 2 pi. Here's 2 pi. But I want to exclude all the places where I have the vertical asymptotes.
Okay. Thank you.
You're welcome. That's the same thing we did for the cotangent one, and then also a similar thing we did for the tangent one. All right, one more trig graph. We're almost done with them. I know it always takes a long time to graph all the trig functions, but it is good to have seen them so that later on when we talk about their graphs, because we will refer back to their graphs for various reasons, it's good to be like, oh yeah, I know what that looks like. I have an idea of how that looks. So let's graph secant of x, which is 1 over cosine of x. Oh, I forgot one thing on the previous one. It's not a huge deal, but let me ask you all. All right. Even or odd? Well, not even again. And here's how we know it's not even. The thing right here doesn't have a mirror image right there. It's odd. If you reflect it in both axes, it looks the same. Or if you even though it's weird to rotate this thing, if you rotate this thing 180 degrees, it really does look the same. But you can also just check, right? If you do cosecant of negative x, that's 1 over sine of negative x. But since sine is odd, sine of negative x is negative sine of x, but that ends up equaling negative 1 over sine of x, which is negative cosecant of x. So cosecant is definitely odd. In a similar way, since cosine was even, we are going to see that secant is going to be even as well. Or as I like to remember, of all 6 trig functions, cosine and secant are the only even ones, and the other 4 are odd. I do want to make sure, though, that I'll show you an example in a minute. Everyone's clear, or at least maybe clear on the fact that not every function has to be even or odd. All the trig functions are either even or odd, but there's lots of functions that are neither, which we'll see examples of in a minute here. All right, one more. So we'll graph cosine. Well, I'll show you how I really do it. So I'm going to go 0 to 2 pi on both sides, or negative 2 pi, and then cut it up into 4 equal quadrants. I'm not actually going to graph cosine. I'm just going to hit the highs and the lows and the middles. So cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1. I guess I could label these as well. And then same to the left. Cosine of negative pi over 2 is 0. Cosine of negative pi is -1. Cosine of negative 3 pi over 2 is 0. Cosine of negative 2 pi is 1. So then I know whenever cosine is equal to 0, 1 over cosine is going to have a vertical asymptote. So I'm going to have a vertical asymptote here at 3 pi over 2, here at pi over 2, here at negative pi over 2, and here at negative 3 pi over 2. Again, those aren't the only ones, right? Those are just the ones we happen to be graphing. There'd also be one at 5 pi over 2 and 7 pi over 2 and every odd multiple of pi over 2. All right. If cosine is equal to 1, secant is equal to 1, cosine would go down to 0, secant's going to go up to infinity. Same thing on that side. And then down here, cosine would go back to 0, secant's going to go away from 0, down to negative infinity. You're never crossing the x-axis. You're always going away from the x-axis. So here, since I'm starting below the x-axis, I'm going to go away and below. Should be a little more rounded than I've drawn it there. Instead of going down, I'm going to go away and up. So there's a couple periods of secant. The range is the same as it was for the cosecant function. It's everything from negative infinity to 1, negative 1, union 1 to infinity. The domain is the same as it was for the tangent function, right? Just like tangent is sine over cosine, secant is 1 over cosine. They're both going to be undefined whenever that cosine is equal to 0, which happens to be all odd multiples of pi over 2. So it's negative pi over 2 plus a multiple of pi to positive pi over 2 plus an integer multiple of pi, where k is an integer, where k is an element of the group Z, the set Z, not group, sorry. And then secant of x is an even function. It has that symmetry across the y-axis. If you flip this across the y-axis, it looks exactly the same as it did before. Cool. It's all 6 trig functions. There's one more thing I want to say here. And just like I said for tangent, all 4 of these trig functions that we just graphed, not sine and cosine, but, well, I mean, also sine and cosine, but specifically tangent, cotangent, cosecant, and secant, they are all continuous on their domains. They are all differentiable on their domains. So are sine and cosine. Their domains just happen to be everything. Sine is continuous and differentiable everywhere. Cosine is continuous and differentiable everywhere. Just domain. Okay, how much time? Okay. How many of these functions are invertible? Are any of them invertible? What does it mean to be invertible? Right. So let's look at another example and then we'll come back to this. So we'll get a few. Yeah, we got time. Okay. So is y equal to x cubed invertible? Oh, I'm not asking you. Okay. So what does it mean to be invertible? It means that we can interchange the role of x and y and still get a function. Some things are not invertible when we do this. We can fix that though. So let's see. So if I switch x and y, or interchange, but switch is easier to write. I get x equal to y cubed. And while I could solve for y, and I will solve for y, I'm just going to graph this. So here's y equal to x cubed first. It looks like this. This is not my favorite function to graph. I'm not really good at it. Ish. Okay, it's all right. There's y equals x cubed. You've got points like 1, 1, and 2, 8, and -1, -1, and -2, -8, and other points that are not nice. And if I graph x equal to y cubed, I'm just doing the same thing, except now I'm kind of pretending like my axes are flipped. So instead of x being 2 and y being 8, y is going to be 2, and x is going to be 8. Instead of, well, 1, 1 is still a point. I still get 1, 1. I still get 0, 0. If y is -1, x is -1. If y is -2, x is -8. And literally, what's happening here is I am literally interchanging all the xy coordinate pairs. On this graph, I would have the point 2, 8, 1, 1, 0, 0, -1, -1, -2, -8. And I'm just changing the x and y positions. So it's going to look kind of like this. Kind of because, you know, my graphing skills. Ooh, wow. Yeah, kind of. Hard emphasis on the kind of there. Yeesh. Yeah, not my best. So there's x equals y cubed. Or if you want to solve for y, take the cube root of both sides, you get y equal to the cube root of x. So y equal to x cubed definitely is invertible. Because when we find the inverse relationship, it's a function. It passes the what test? The vertical line test. On the other hand, is y equal to x squared invertible? Well, let's graph it. Easy enough. There's good old everyone's favorite parabola, y equals x squared. It means my favorite parabola. It might not be yours. Everyone should have a favorite though, so go pick one when you're. I'm gonna ask you on Tuesday what your favorite parabola is. You can come up with something else if it's not y equals x squared. Let's invert them. I probably won't really ask you, but if we graph x equal to y squared, which happens to be on the board, it looks like this. Is that a function? No. Now I should be more clear. In the context of this class and most of the 21 series, when we say is something a function, we explicitly mean is y a function of x. Because you could certainly take this in a different context and say, yeah, James, it's a function. X is certainly a function of y here. Each y input gives you one x output. But that's not the question that's meant. The question that's meant is y a function of x? And the answer is a resounding no. Why not? What's one good reason? What does it fail to do? Right. Fails the vertical line test. Now, there's another way I'd like you to think about this or to know about this because I think it's a little bit more useful. You're not always going to have a graph. You're not always going to see graphically that something fails a vertical line test. Another way of knowing that this is not a function is that one x input gives you multiple y outputs. Hint or fun fact, that's the same as failing the vertical line test. One x input, like x equal to, let's pick a nice number like 9, gives you two distinct or more y outputs. Y could be 3, y could be -3. That is the very definition of failing to be a function. Because to be a function, it should be the case that each distinct input gets assigned one and only one. No, not the only one output. So going back over here, for this function to be invertible, its flip has to pass the vertical line test, which means it has to pass the, yeah. So if your function fails the horizontal line test, it's not invertible. Not invertible. Until we fix it. it fails the horizontal line test. In other words, it fails to be what we call one-to-one. A function is one-to-one if two different x inputs give you two different y outputs. And that's not the case here. Two different x inputs, like +4 and -4, give you the same y output. So it's not one-to-one. All right, so now, real quickly, just looking back for a moment at all the graphing we've done. Is that function invertible? Does it pass the horizontal line test? No, hard no. What about this function? Is this one invertible? No. How about, no, that's not one of them. How about tangent? Does it pass the horizontal line test? So if I draw a horizontal line, does it go through more than one point? Definitely. Does it pass the horizontal line test? No, it does not. Right, to pass the vertical line test, any vertical line should only go through one point at most. To pass the horizontal line test, any horizontal line should go through at one point at most. So does it pass it? Definitely not. How about that one? How about that one? How about that one? None of them are invertible as it stands. But we know how to fix things. So here's the deal. Even though none of the trig functions are invertible as they are originally drawn, there is an inverse trig function for every trig function. You've probably seen them on your calculator. There's an inverse sine, sine to the -1. I should say that's not the same as 1 over sine. We know what what's 1 over sine? We just drew it a minute ago. Is it secant or cosecant? It's cosecant. It's definitely not the inverse sine, which is a totally different thing, which is why I like to use a different name for it, because it's a little confusing. Okay, but before we do that, how much time have I got? I got enough, yeah. Before we do that, this is invertible. I just have to fix it first. So the real answer to is y equals x squared invertible is yes, if we limit or restrict the domain so that we are working with something that is one-to-one. Or something that passes the horizontal line test. So here's what we're going to do. We're going to say y equals x squared is our function, and we're going to limit our domain to x being greater than or equal to 0. You could also pick x being less than or equal to 0, but that is definitely the non-standard choice. So here is my new function, y equals x squared, but only when x is greater than or equal to 0. Here's the other half of it that we're not going to worry about, that would cause it to be not one-to-one. So now when I invert it, look what happens when I invert it. I know we haven't really talked a whole lot about how you invert a thing, but basically you switch x and y and you solve for y. So I'm going to switch x and y. So x is going to equal y squared. And I'm also going to switch x and y in the domain. Because when you interchange x and y, all the things interchange. The domain array, that in fact, that's how you find the range of functions. Is you find, if you can, you find the inverse of your function and then find the domain of your inverse. You find the range of your original. It's kind of cool. So here, we're going to get that. All right, now I want to solve for y. Or actually, I just want to draw it. So x equals y squared, but now I'm only getting the top half because y has to be greater than or equal to 0. I'm not getting this bottom half that was there before. Wait, can I draw it? Maybe. Hey, look, that blue part is just a function. Not just a function, is a function. It passes the vertical line test because that red part isn't there. And maybe I shouldn't even draw it. You could also say that this is y equal to the square root of x if you wanted to solve for y. So this function is invertible if we make the additional step of limiting the domain of the original function to something that is 1-to-1. I will point out that this piece down here would be y equal to the negative square root of x. But we're not including that when we're talking about just inverting that part there. Okay. The reason I mention all this is because that's how we do it for all of the trig functions. Every single trig function has an inverse if we take the time and care to first limit the domain of the original function and then find the inverse of the resulting thing. Sometimes that results in a function that's pretty small. Let's look at, we have time for one example. Let's look at sine, because that's kind of the best one. So if I have y equal to sine of x, which has my usual graph, and yes, I do want to draw it again. I don't really want to, but I should. Okay, there's most of a couple periods of sine. So when you're inverting a function, or I should say inverting the relationship to get a new graph, you're just changing x and y. So if I invert, I'm going to get x equal to sine of y. Now, if I just graph that, it's not going to be a function. It's going to look like the sine graph, but on the y-axis instead of on the x-axis. In fact, all I'm really going to do to graph this is I'm going to interchange all the points. So instead of 0, 0, I get 0, 0. Instead of pi over 2, comma 1, I get 1, comma pi over 2. Instead of pi, comma 0, I get 0, comma pi. We'll do one more up. Instead of 3 pi over 2, comma negative 1, I get negative 1, comma 3 pi over 2. I'll go down a little bit too. I get negative pi over 2, comma negative 1, or I should say negative 1, negative pi over 2. So here is what my x equals sine of y looks like. And it's kind of hard to draw. Shouldn't be that hard to draw. Definitely not a function. So here's what we're going to do. We're going to limit the sine function to this domain right here. Everything from negative pi over 2 to pi over 2. Because from negative pi over 2 to pi over 2, you don't have any repeats of your y values. Or I should say, that section right there, that section will pass the horizontal line test, which means the corresponding section over here will pass the vertical line test. So here's the graph of y equal to the, I'll say it, but I don't love it, the inverse sine of x, or alternatively, but equally good, in my opinion, preferable, y equal to the arc sine of x. It looks like this. So you've got these 3 points are what I want to focus on. 1, comma, pi over 2 is about 1.5, 0, 0, and negative 1, negative pi over 2. Lesson. Here is our inverse sine graph. Kind of not a lot, but that's the whole story. It goes from negative 1, comma, negative pi over 2 to 1, comma, pi over 2. I got a few minutes, okay. Inverse trig functions are a little bit weird. What do I mean by that? Well, if I said, what's the inverse sine of, say, I don't know, root 2 over 2, I'm asking you, what angle do I take sine of to get root 2 over 2? Pi or something. I mean, you could say degrees, but we should say radians. The angle is pi over 4. The sine of pi over 4 is equal to root 2 over 2. Okay, I'm gonna ask one more. What's the, I prefer arc though. What's the arc sine of -1/2? Good question. So sine of what angle? Let's ignore the negative for a second. Sine of what angle equals +1/2? Pi over 6 or is it pi over 3? Pi over 6. Okay, so sine of what angle equals -1/2? Yeah, it's not 11 pi over 6, although those angles are coterminal. We specifically have to use the angle that is between -pi over 2 and pi over 2. Why? Because someone decided that was going to be what we're going to use once upon a time. For no other good reason other than it looked like a nice choice. But really, someone could have defined it a different way back when, and then we'd be doing a different thing. But we specifically decided that this is going to be -pi over 6. The lovely thing about arc sine versus the other arc cosine is that positive ones give you positive answers, negative ones give you negative answers. So if you know that the arc sine of root 3 over 2 is positive pi over 3, you automatically already know that the arc sine of negative root 3 over 2 is negative 3. Again, not something we need to spend a whole lot of focus on, but I did want to spend a little bit of focus on talking about the inverse relation. So have a lovely 3-day weekend. I'll see you all on Tuesday. Don't come to school on Monday. There is no school on Monday.